Hey guys, welcome back to another RASK maths tutorial, and in this tutorial I'm going to be talking about stationary points and polar coordinates, following up from yesterday's videos where I just talked about general stationary points. So on the Cartesian plane, a stationary point is basically just when the curve is either turning or it's a point of inflection. But generally when we talk about stationary points, we usually want to talk about turning points, which are the minimum and maximums you see here. So this would be a maximum and that would be a minimum. So yeah, it's pretty simple on the Cartesian plane, but on the polar plane, stationary points become a little bit more complicated because obviously if you're just measuring from the radius and the angle, then the points are always turning because the x in polar coordinates is essentially just the angle theta it's making. So what are stationary points in polar coordinates? Well, I'm going to show you a really bad example. If we have a circle in polar coordinates, this is just the equation r equals 1 because the radius is 1 for any angle theta. Now, to find the stationary points in polar coordinates, we use the same sort of techniques. So we're going to differentiate to get r dash equals 0, and then stationary points is equivalent to finding when r dash is equal to 0, which is true for all r. So therefore, it's essentially saying all values of theta are a stationary point. And hopefully that makes sense because you can see here that since this is a circle, every single point is going to be turning and changing. So that's why every single point is considered a turning point, like so. Because if you imagine, that's a turning point, that's a turning point, that's a turning point. Everything is a turning point on this. And I'm going to show you guys another graph which actually has some more defined stationary points. So it's the graph of r equals 3 plus 2 cos theta. And I'm going to probably do a bad drawing, but it looks something like this. So it comes around, it dips, and then comes back and does that. Just like that. This is actually symmetrical around this line, but I've just done a bad drawing. But yeah, you can see that we have two stationary points. We have a stationary point here and a stationary point here. And the reason I picked this graph is because these actually are the two different types of stationary points. So we could call this one a maximum, and we could call this one here a minimum, putting them in inverted commas because, again, whenever we talk about stationary points in polar coordinates, they're always a bit weird. Now, when you differentiate, what you're really finding is r dash, which is the change in r over the change in theta, so dr by d theta, and we differentiate using the same sort of thing. So 3 is a constant, disappears, and then it just becomes minus 2 sine theta using the chain rule. Sorry, not chain rule, just derivative of cos is minus sine. And then we want to solve to actually find these stationary points. We use r dash is equal to 0, so that's going to mean minus 2 sine theta equals 0, and that means we're going to have solutions at theta equals 0, pi, and 2 pi, which is actually just the same as 0, so we can ignore that one. And I'll put these as degrees in case you guys don't know what the radians are. So 0 and 180 degrees. You can see this corresponds perfectly with this line here, which is 0 degrees, and this here, which is pi r, or 180 degrees, like so. And we got a minimum and maximum. So stationary points on polar curves are essentially the same thing as on a regular curve, except see how up to here, the r is consistently getting bigger, and then once we reach the maximum, that's the maximum value of r, so it starts to get smaller again, till it reaches its minimum over here, and then it starts to get bigger again. So that's basically what it's saying. The change in r as theta changes is 0, and you can see the change in r is getting smaller and smaller, still increasing, then at the stationary point it's 0, and then it starts to reduce. So just the same thing as in the Cartesian plane, but just a bit more confusing now. And we can use the same sort of tricks as we use on the Cartesian plane to figure out the nature of these stationary points. So let's say determining the nature. Also, I think I spelled determining wrong. Determining the nature of these stationary points. And to do that, we use the second derivative. So we're looking at the rate of change of dr by d theta. And second derivative is going to just be minus 2 cos theta. Now, if we put theta equals 0 into here, so r double dash when theta equals 0, we're going to get minus 2 cos of 0, which is just minus 2, which is less than 0. So therefore, this is going to be a maximum. If you don't know where this comes from, you should watch the video on the Cartesian stationary points, but you can see that we've concluded that's a maximum. And if we find what r dash is when theta equals pi, then that's going to give minus 2 cos of pi, which is simply minus 1 times minus 2. So that's 2, which is greater than 0, so therefore it's a minimum. So hopefully you can see how the minimums and maximums in polar coordinates are essentially the same thing as the minimum and maximums in Cartesian equations, but now you also have to account for the rotating graph, so it's less defined. I'm going to show you guys one more graph, and this one is much clearer to see these stationary points. It's the graph of cos of 3 theta, which looks something like this, if I can draw it right. Yeah, so it looks something like this. This is r equals cos of 3 theta. And you can see we actually have 3 stationary points here. But what you'll notice is there's actually 3 more stationary points coming in like this, because r is progressively getting smaller and smaller until it reaches the origin, at which point r is 0. So there's actually going to be 6 stationary points, but 3 of them are going to be at the origin, so 4 in total. And we can find these using the same technique, so minus 3 sine 3 theta, solve for when r dash equals 0, so we get sine of 3 theta equals 0. Now we can solve this using 3 theta equals, so we're going to have 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, and 6 pi is just going to give us 2 pi, which is the same as 0, so we can ignore that. So our solutions for the turning points are 0, 1/3 pi, 2/3 pi, pi, 4/3 pi, and 5/3 pi. And you can see these correspond nicely. So this is the 0, 1, 1/3 pi. Well, that's effectively going to be this one here, the minimum. And 2/3 pi, that is going to be this one. 4/3 pi, again, that's going to be, so r's coming here, it's steadily reducing, and then it reaches the stationary point right there. So that's the 4/3 pi, 5/3 pi one's this one, and then, no. The pi one is the minimum again, and then the 4/3 pi one, well, that's going to be this one here, and then again the 5/3 pi one is this minimum. So these are alternating between minimum and maximums, with the minimums being at 1/3 pi, pi, and 5/3 pi, and the maximums are at 0, 2/3 pi, and 4/3 pi. Hopefully it's clearer how these stationary points work. Thanks for watching, and I'll see you guys in a future tutorial. Bye!